Right, so which ones do you need me to do?
Number one, you said you would explain.
Yeah, I think that'll actually come up in a slide later in the chapter, so I'll do that when it comes up. That's the Brownian motion, isn't it?
Number 7.
So, which one?
Number 7.
Number 7, okay. Can you read number 7 to us? Can someone read number 7? Okay, you're going to read it, Beto?
Yeah, it says a flask A of volume 2.23 times 10 to the power minus.
Okay, let me just draw that. So this is flask A, and its volume is?
2.23 times 10 to the power minus 3 meter cube.
Okay,
Is connected to flask B
okay,
of volume 1.65 times 10 to the power minus 3 meter cube.
like this?
Yeah.
Okay,
By a length of tubing of negligible volume.
okay,
A tap in the tubing is initially a tap in the tubing is initially closed.
Mhm.
Flask A contains 0.254 moles
254 moles.
of an ideal gas,
Mhm.
and flask B contains 0.352 moles of the same gas.
353.
352 moles of the same gas.
Okay,
The tap is then opened,
okay,
enabling the gas to flow between the two flasks, and the temperature stabilizes at 20.3 Celsius.
20 point.
3 degrees Celsius.
Okay,
Determine the number of moles of gas now in flask A.
okay. So if we think about our PV equals nRT formula, we can apply this to the two different flasks. We have PV equals nRT and PV equals nRT. Now, when this is open, we know the temperatures are the same. They're both 20.3 Celsius. We also know that the ores are the same, and the pressure will be the same, although we don't know the pressure. And we know the volume. So I'm thinking what we can do, if I rewrite this equation, I can say the pressure in A is nRT over V,
Yeah.
and the pressure in B is nRT over V, and they must be equal. The pressure must be equalized. But the problem is I don't know how many are in A and I don't know how many are in B. So I'll say N1 times 8.31 times 273 plus 20.3 over 2.23 times 10 to the minus 3. That should equal N2 times 8.31 times 273 plus 20.3 over 1.65 times 10 to the minus 3. And what's kind of interesting is that it doesn't seem like the temperature matters, because that and that cancel, that and that cancel.
But the N was given, wasn't it?
No, well, not how much is in each of them after the tap's opened. So you could and these cancel. So you can rewrite this as 1.65 N1 minus 2.23 N2 equals 0. Exactly. And also N1 plus N2 should equal 0.606, is it?
Yeah.
Now, what situation have we got here?
So it was
It's adding the 2 here at the beginning. None of the gas escaped flask A and B. So the total number of moles has to be the same. Is it 606?
Yes.
I think the easiest way to... well, actually, they are just looking for N1, aren't they?
Yes.
So the easiest way to solve this would be to multiply this by 2.23. So what do you get here? That's 2.23 2.23, and what does this become?
1.35.
Say again?
1.35.
1.35. 351. Okay, so if I add these together, I get 3.88 N1 equals 1.351. So 1.351 over 3.88. That's the N1. What's that now? 0.348. 0.348. Okay.
Yeah.
I think it's interesting. We didn't need the temperature, did we? I didn't need the pressure. Now, we assumed the pressure was equal after we opened the tap. We also assumed that the temperature was equal. It seems perfectly reasonable to assume that when the two gases mix together, they reach a common temperature. But I don't think the question explicitly said that, did it? Stabilizes. Okay. Fair enough. Okay.
Then 12C. 12C.
12C. What are we asked for there?
Well, it's like. I'm sorry, 11C.
Yeah, what's it asking for?
Suggest the reason why cylinders for storing gases at high pressure are tested by filling them with pure water under pressure rather than with high pressure gases.
I can think of one obvious reason is if you test the cylinder by filling it with water, that's kind of safe. Because if the cylinder cracks, all that's going to happen is water leaks out. You wouldn't want to test it with something like, I don't know, hydrogen. You know, that's one reason. Second reason, water's cheap. Third reason, I think, no, that's two good reasons, I think.
So if I say water is cheap, I'll get my money.
I think that's a fair enough reason because, you know, if suppose you're your company, right, and you're building cylinders that contain materials, and you want to test that the cylinder is safe, well, why would you pay lots of money to fill it with an expensive gas when you can just fill it with tap water? Do you know? But I have a feeling that the answer that they were really looking for is that it's safe. Okay.
Number 17.
What's 17 asking you?
An atom of argon moving at a speed of 320 meters per second
Yeah.
hits a surface at right angles to the surface and rebounds at the same speed in the opposite direction.
Yeah.
The impact lasts for 0.186 nanoseconds.
Yeah.
So determine the mass of the argon atom.
Yeah.
The relative atomic mass of argon is 40.0. Determine the change in momentum of the argon
Now,
atom.
what part of that couldn't you do, Bello? Because what did they say? What did they say the atomic mass number was?
40.
40. Now you know from chemistry what that means, don't you?
Yeah, I remember it's supposed to be mass over.
Yeah, so could you use that to calculate the mass? Am I right in thinking, guys, in this question they said the mass, what is it, 40? Is it? Yeah. So that means 40 grams is the mass when you have 1 mole, isn't it? And they want the mass of 1 atom. So 40 grams is the mass for 1 Avogadro's worth of the atom. So to me the answer is just simply 0.040 divided by 6.02 times 10 to the 23. Done. That's the mass. You know this from chemistry, right? Yeah. And what's the next part?
So we change the momentum of the.
Okay, so the change in momentum is mv minus mu. Yeah. Do we know the m? Yeah, it's right there. Do we know the v and the u? Yeah. What's the speed? Did you say 300? 320. So minus 320 minus 320. Because the u is positive 320 and the v is minus 320. Bounces off the wall. So the change in momentum would be 0.040 times minus 640 all over 6.02 times 10 to the 23. Any more to it?
Tell me the average force of the
Okay, and how do you get that, Bello?
and the
How do you get the force?
this
No. Know the formula? How do we get the force here? Do you know delta P? Do you know delta T? Job done.
just hold up.
Anything else? What's 21 about?
Actually 19 from 19, 20 and 21 are all like the same and then they have like an issue.
19, 20 and 21 are all the same.
Yeah, they have the same issue.
They have the same issue. Okay, we'll do 19 then, if they're all the same.
Like the last question in 21.
What's it to say?
Six,
Oh, one at a time. Okay, he's telling me. Yeah, last one in 21. What's he say? What's to say?
whether the number of molecules would be more or less or the same if the temperature will be hydrogen gas instead of air at the same temperature and pressure.
Okay, fine. Let's have a look at that. So you have PV equals nRT, right? So N equals PV over RT. Now, the tire is filled with what instead?
The hydrogen gas.
Instead of
Air.
air. Okay. It kind of looks like it'd be the same because the tire pressure you would keep it the same, right?
Yes.
The volume you would keep it the same. I think it would be the same because I don't think any of the PV or RT changes. I think it's the same. Yeah. Assuming when you put the hydrogen in, you keep everything else the same about the tire. The tire pressure stays the same, the volume of the tire stays the same, and the temperature of the tire stays the same. So if the tire is at, for example, the tire's temperature would be whatever the temperature of the outside is. The pressure you have to keep the same, whatever the pressure is. I only know what it is in pounds per square inch. It's like usually 30. And the volume. Yeah, okay, I think it's the same. I think it's the same. Yeah. Say again? What do you mean? They don't answer it? in the marking scheme.
Yes.
They just say,
The same.
Yeah, just say it's same, but I don't know what it's saying. The answer just say it's same.
oh yeah, that's what I'm saying. The M is the same. It doesn't change.
Calculate it to give it the same value. Well, me, I had like.
Oh, you calculate. No. It's probably only like 1 mark. They probably
Yeah,
just.
like, no, the questions following up. That was like the last
That's
question.
Yeah.
the last question.
Yeah,
There were like some calculations.
yeah, fine.
Like in the question it says 2.2 atmosphere. That is 2.2 times 1.01 times 10^5. But they use 3.2. I don't know. Like I checked the answer.
Oh, maybe it's a typo mistake. You think they used the wrong number?
Yeah.
It's possible, yeah. They gave one number in the question, and they used a different one in the answer. Yeah, okay. That sometimes happens.
They didn't show the conversion, so that's why I was confused. Like they didn't do a value times the constant.
Oh, right, okay. They just gave the
gave
answer.
the answer.
Yeah,
So
okay.
I don't
Okay.
know if there was something I missed in the.
Well, we can check it, but just 1 second, yeah.
Yeah.
Yeah, but when you use the ideal gas law formula, for the M to be different, one of these 4 has to be different. You know what I'm saying? So can you tell me which of these 4 numbers, well, it's definitely not going to be OR, right? So which of these 3 numbers could be different? You see what I'm saying? Yeah. Yeah. So, but my question is, if the n is different, then one of these 3 numbers have to be different. So my question is, which one? Yeah. Yeah. I can't, it's really hard for me to see how it could be different. Now you would need to demonstrate with a different formula how it could be different.
Yeah, like it says helium and hydrogen. Hydrogen is like in air, and air has other things. So I think that will change the mass.
Yeah, but it won't change the number of moles. Yeah, like the volume, maybe. The volume, to me, the volume is the only one that could possibly be different. Volume is mass over density. So the density will be different for the different gas, but the mass would also be different. So the 2 might cancel each other out. You get what I'm saying? Anyways, the question doesn't give us any numbers, does it? Like it's only a 1 mark question, is it? Yeah. Yeah, I think it's the same. Well, sure, the answer says it's the same, and that's what I thought anyways. So, now in real life, maybe in real life there might be a tiny bit of a difference. Maybe the volume changes slightly, because in real life things behave not as nicely as the formulas would suggest, Like for example, if you put helium into the tire, for example, the number of moles would be the same, but I suspect that the number of moles would quickly start to decrease because the rubber tire wouldn't be able to hold the helium as well. So in real life these things would perhaps change, but according to our formulas which we're using, they would not. Okay, I really need to start the lesson, guys, because we're coming up to like nearly 11:25. So we'll have to go on to the next topic now. Okay, but if you got 19 or 20 questions done, that's excellent. Okay, that's good. So, if you got 20 questions done and only 10% of them were a problem, I'd consider that a great success. Okay. You can see that they like this question in the exam. It's very, very